Hello friends, welcome to Talent Spare's Entrance Academy. I am Dr. Sandhya Kumari L here to help with your chemistry lessons. So let's start with our Unit 1 solid state of class 12. We all know that solid is a state of matter in which the constituent particles are so closely packed. So the constituent particles can be atoms, molecules or ions in different types of solids. So talking about the properties of solids, we know that they have definite mass, volume and shape, and solids are non-compressible and very rigid. Then the intermolecular distances are so short and hence the intermolecular force of attraction are so strong because they are so closely packed. The constituent particles have fixed position in their lattice point and hence they can only vibrate about their mean positions. So these are the properties of solids. Let's move on to the classification of solids. Based on the arrangement of the constituent particles, solids can be broadly classified into two types. They are amorphous solids and crystalline solids. As you can see here, the crystalline solids have a definite orderly arrangement, whereas there is no definite orderly arrangement in the case of amorphous solids. Let's look into the details of these two types of solids. So first one is the crystalline solids. So as you can see here, crystalline solids have a definite ordered arrangement. So hence they have a definite geometrical shape, as you see in the case of sodium chloride, diamond and all kind of crystalline solids. And that order is in long range order. So when you take a crystal, the orderly arrangement will be for a long range. And hence the property, if you look at the property, some of the properties of crystalline solids, due to this orderly arrangement, they have very sharp melting point. Then another interesting characteristic of a crystalline solid is that they are anisotropic in nature. Anisotropy means if you measure some property, for example say refractive index or electrical conductivity or any physical property, when you measure it from one particular direction of a solid, it will give a different value, and when you measure it from some other direction, it will give a different value. So that means the physical properties show different values when measured along different direction in the same crystal. That is what is called anisotropy. And here also they have definite and characteristic heat of fusion due to this orderly arrangement in the case of crystalline solids. In fact, crystalline solids are called the true solids. So when we say solids, it will be crystalline solid. And when we cut a crystalline solid with a sharp edged tool like knife, they split it into two halves. So the newly generated surface will be very plain and smooth. And examples, you definitely know the examples of crystalline solids. They are table salt, diamond, copper sulfate, zinc sulfate, all those are crystalline solids. Now, the same crystalline solid can show different crystalline forms. For example, one single substance can show two or more different crystalline forms. For example, carbon. We all know that carbon. Carbon exists as graphite, also it exists as diamond. That means it has two different crystalline structures. So this is the structure of diamond and this is the structure of graphite. Those two structures are different. So carbon can exist in two different crystalline forms, and hence that type of crystalline forms are called polymorphs or polymorphic forms. So example is graphite and diamond. Let's see the difference in the properties of these two polymorphs of carbon, because diamond and graphite are crystalline form of the same substance, but still they have entirely different properties. So both are crystalline. So it has a crystalline lattice, but it has a layered structure. Even though both are crystalline, it has a layered structure. So that difference in the structure makes the difference in properties of these two compounds. In the case of diamond, each carbon is sp3 hybridized. This is a very important point. Whereas in the case of graphite, each carbon is sp2 hybridized. sp3 hybridized means there is only sigma bond in diamond. Whereas in the case of graphite, each carbon is sp2 hybridized. That means there will be sigma bond as well as pi bond in it. And here diamond will be made up of tetrahedral units, whereas it has a planar geometry. And if you look at the bond length, carbon-carbon bond length in these two crystalline forms, in the case of diamond it is 154 picometer, whereas in the case of the bond length, CC bond length in the case of graphite is 141.5 picometer. So, due to this crystalline lattice structure, it has a rigid covalent bond network, and that makes diamond the hardest known substance. It's the hardest naturally occurring substance, diamond. Whereas graphite, it is also made of carbon, but graphite is very soft, and we know that graphite is used as a lubricant, right? Because it has a layered structure, each layer can slide over one another. That's why it is very soft and also used as a lubricant. Another important property is that this is an insulator. That means it does not allow electricity to pass through it. It's an insulator, whereas graphite is a good conductor of electricity. So you see, both are crystalline, but based on the difference in the structural arrangement, they have entirely different properties. Now let's look into the details of amorphous solids. As I already said, amorphous solid does not have an orderly arrangement. So they don't have a regular shape, they have an irregular shape. And even if you see some of the order in some crystalline, some amorphous solid, they will be for some short range. For example, glass may appear like it has an orderly arrangement, but that orderly arrangement we can see only for some short range. And they usually soften on heating. Like rubber, we know that rubber, when we heat rubber, it will become soft. And another interesting property is its isotropic nature. That means when we measure a physical property, when we measure it along all direction, it will give the same value. So it's the opposite of anisotropic. And when we cut an amorphous solid with a sharp edge tool, they cut it into two pieces with the irregular surfaces. And they do not have, these amorphous solids do not have a definite heat of fusion. And they are not true solids, they are actually called pseudo solids. Pseudo means not real, or we can also call them as super cooled liquids. Why we call as liquids? Because some of these amorphous solid has a tendency to flow. For example, when we melt glass, it can slightly flow, not like liquid, but still it can flow to some extent. So that's why it's also called super cooled liquids. Examples are glass, plastic, rubber. So all these are amorphous solids. So we have seen the broad classification of solids, that is amorphous and crystalline solids. Now let's move on to the classification of crystalline solids. Crystalline solids can again be classified into four types. One is the covalent or network solid, then metallic solids, ionic solids, and finally molecular solids. These covalent network solids can again be classified into two types, two-dimensional solids and three-dimensional solids. Then molecular solids are classified into three types. One is polar solid, next is non-polar solid, and the last one is hydrogen bonded solids. Let us look into the details of these type of crystalline solids. So let's start with the molecular solids. So as I already said, there are three types, non-polar, polar and hydrogen. So in the case of molecular solids, the constant particles will always be molecules. In that solid, the constant particles are molecules. In the case of non-polar solids, the molecules are held together by London forces, whereas in the case of polar solids, the force of attraction will be dipole-dipole interaction. And in the case of hydrogen bonded solids like ice is a solid like molecular solid. So there, each water molecule is held together by hydrogen bond. So you can see the examples here. Iodine is a non-polar solid, hydrogen chloride is a polar solid, whereas ice is a hydrogen bonded molecular solid. And you can also see the physical nature. Usually they are soft, but hydrogen bonded ice is a hard solid. And if you see the electrical conductivity, molecular solids will usually insulated, they will not conduct electricity, and their melting point is usually low. Next, move on to the ionic solids. In the case of ionic solids, the constant particles will be ion, positive and negative ions. So in these solids, these ions are held together by strong electrostatic force of attraction or Coulombic force of attraction. So examples are sodium chloride, magnesium oxide, zinc sulfide, etc. They are hard but brittle. We can easily break them. They will conduct only in molten state. They do not conduct in the solid state, but they can conduct electricity only in the molten state or in aqueous solution, and their melting point will be usually high. So in the case of the third type is metallic solid. In the case of metallic solids, there will be metal ions and they will be surrounded by it will be like metal ions dispersed in a sea of electrons. So there will be metal ion, positive metal ions, as well as free electron in the case of a metallic solid. So they are held together by metallic bonding. Examples are metals like iron, copper, silver, etc. So they are usually hard, they are malleable and ductile. That means they can be drawn to thin wires and they can be hammered to thin sheets. They are usually conductor. They conduct in solid state also, and their melting point will be fairly high in the case of metallic solids. And the last category is covalent solid. In the case of covalent solid, what will be the constituent particles? Yes, atoms will be the constituent particles, as in the case of diamond and graphite. Examples are diamond, graphite, silicon carbide, silicon dioxide, etc. So their force of attraction is covalent bond. Each carbon will be held together by strong covalent bond. So some solids will be hard and some will be soft. For example, graphite is soft whereas diamond will be hard. It depends. It depends upon the solid and the bonding in them. And usually they will be insulator like silicon dioxide, diamond, they are all insulator. One exception is graphite, which is a good conductor of electricity. And if you look at the melting point, they will be very high in the case of covalent solids also. Now let us clearly understand what is the structure of a crystalline solid.